All right, thanks for waiting. Okay, so is it time? Yeah. So I'm going to start this by a brief review of what in-context learning is, and then we'll do a little bit of mathematics and try and talk about what it means for understanding in-context learning in the situation of singular learning theory and statistical learning theory in general. So before we get started, some reasons to care about in-context learning very briefly. So this is one of the emergent capabilities of transformer models. It's what underlies some of their capabilities. We don't have a good understanding of why it emerges or what exactly it is. Just one second. And we would like to understand how it seems to be that transformer models are capable of many different tasks within one model, and the role of in-context learning in selecting tasks by providing context is the key to that. So if you'll follow me around to this other set of boards, I'll just remind you of the architecture of transformers briefly, so please follow me. Okay, so here I'll just recall from the Fong-Hada paper the decoder-only form of the transformer. So it takes in entities, processes entities, its input tokens, so sequences of tokens. Those are mapped through, I think the diagram is over here. These are mapped through an embedding layer, which changes those tokens into vectors. Entities. Those entities are then processed over multiple transformer blocks. Then there's an unembedding layer, a linear transformation on each of those entity vectors. So each vertex in this diagram on the right-hand board stands for an entity vector. And then there's a softmax applied to that final vector, which produces a distribution over all possible tokens. And then you make a prediction about the next token. So in the transformer model, there are many different ingredients. There's layer normalization, there's multi-headed attention, and there's a feed-forward layer shown here at the bottom on the right-hand board. I'm going to ignore the role of that layer normalization and the feed-forward layer and focus on attention and only a single head for the purposes of today. Okay. I think there should be on one of these boards something with a context. Yeah. Right, so this was some time ago. We discussed what in-context learning is, and we had this example. So basically, if you provide some initial sequence of tokens and then your question, that initial sequence of tokens is called the prompt or the context, and that's what configures the transformer to be the kind of model that can answer the question given there in green. Okay. So now I think I'm going to begin the story. Just give me a moment. Yeah. Okay, so we'll move over to a fresh set of boards. Please follow me again. Okay. I'm going to set up some notation. So let TW denote the transformer model with attention weights W. Okay, so that the notation from last time, this consists of 3 sets of weights: query weights that transform entities into query vectors, key weights, value weights, and these, of course, may vary between different layers. So this is indexed over all the layers in the transformer. And this is as a family of functions. Where Tn takes a sequence of tokens of length n and returns the prediction of the next token. So as a distribution over tokens. So you might recall from last time that in the definition of the loss function that you'll find in Fwang-Hata or in many implementations, you're given a sequence of tokens, and then there's a contribution to the loss from predicting the next token from every initial segment of those tokens. So if you get a sequence of tokens of length 20, you'll have a contribution to the loss for predicting token 4 from tokens 1, 2, 3, token 5 from tokens 1, 2, 3, 4, and so on. It's equivalent to just consider the case where you're predicting the next token. I mean, you're not taking a contribution from every initial segment. So I'm just going to take the function which returns the probability distribution over token n plus 1 given n tokens. Now, it's important and fundamental to this conversation that a given fixed set of weights W determines this infinite family of functions. Sorry, not infinite. There's a context length. So say 4,000 tokens for the current GPT models. So for n through 1 through 4,000, and for theoretical purposes infinity, let's say, you get a transformer model with the same set of weights. Okay. So unlike usually when we're talking about statistical models determined by parameters, points in a parameter space, for each parameter there's a single model. For transformers, that's not the case. Okay, and that's, as we'll see, somehow one way of thinking about what in context learning is about. Okay.
Sorry, that's a perspective, right? You're just highlighting this perspective. I could equally say that for any function that outputs a sequence, or any model that outputs a sequence, like an LSTM or something like that.
Yeah, it would also be true of an LSTM. That's right. So it's not unique to transformers, but it's maybe an aspect of this kind of sequence model that hasn't been sufficiently well thought about from the point of view of theory, at least as far as I know. And the phenomena of in-context learning is maybe an invitation to think very hard about this, because there's a kind of phenomenon of currying, right, where you can append some initial segment and then get a new model of the same kind. And this, that's, of course, exactly what in-context learning is about.
Yeah, cool. I just wanted to clarify that I'm thinking of it as a perspective, just like a way of mathematically modeling what's going on, where you basically do the currying operation to change what you're thinking of as the function or the arguments or whatever.
Mm-hmm. That's right. I said this out loud, but maybe the notation will come up again. So the contribution of a single sequence, I don't know why I switched to L's, the contribution of a single sequence to the loss. Yeah, in particular, that should be an L. So just a reminder on what the loss function of a transformer is, I guess. So apply the transformer to that input, and then you're going to take the cross entropy. So this is the cross entropy of the sort of one hot vector with a 1 in position xl plus 1, which is the true next token, with the output of the transformer. And that's just negative logarithm, the value of the distribution in position xl plus 1. Okay, so that's at least in direction just the gradient of this entry. We're not going to do much with that, but yeah, that's that. Okay, so now I want to talk about the role of context. So suppose the tokens were examples of a task. And so you think about the first L tokens as being the question and the final token as being the answer. So in-context learning refers to the possibility that on a second question, having the information of the first L plus 1 tokens makes you a better predictor. So suppose you're given a second example. Question rather, which is Y underlined, so that's a sequence of L tokens. Then you have two things you can do. Right? You can take the same transformer, so you can take your transformer and you can feed it that question, then it gives you a distribution over possible tokens YL plus 1. Or you can take, with the same weights, a transformer which takes in the sequence of the given example plus your question, and then returns some other distribution over possible tokens YL plus 1. Now it may be that that cross entropy is actually lower than the cross entropy you get out of this distribution. And you might say that's to do with the example being useful, to learn to predict better for the next question. Okay, so that's one way you can improve your predictor, is, if that's true, to provide the examples. Of course, another way to improve the function, given this information, is to take a gradient step. That is, change W to W plus delta W, and then use W plus delta W to make your prediction. And the papers that sort of stimulated this particular seminar, we're not going to talk really about them directly, because I think they're a bit too flawed to present without further thought in those particular directions that are being explored. But the question they're raising is, can these two things be similar? I think bluntly the answer is no, but it's an interesting question. at least it leads to interesting questions. So the question is these two ways of making use of the example. One is to stick it in the context and by currying get a new function. And the other is to actually take a gradient step and thereby get a new function. Maybe those two functions are similar, and if they were, then you would say that in-context learning is a form of gradient descent. So let me state it as a question, formally. So I'm going to state two questions. First, informally, is there some similarity between in-context learning and learning by gradient descent? Now, of course, maybe providing the prompt just doesn't help you at all. It could be completely irrelevant to the task of predicting the next token on Y, for instance. It may even degrade the performance, right? So it's not like in general you expect any particular relationship between these two things, right? But if these two sequences are drawn from the same distribution, for example, then you might ask this question. Okay, so here's the first form of the question, which is the way I just stated it. So let me state it as a question. Is this function similar to this function? Was the formulation clear to everybody? Now, well, there's a few reasons why you might be immediately suspicious, right? I mean, the gradient step involves a learning rate, but there's no learning rate over here. So certainly for some values of the learning rate, it's absolutely false. Maybe there's some magic value of the learning rate for which it's quasi-true. Who knows? But you can see there's various difficulties in even making sense of this question precisely. So let me pose and then discuss a slightly different question, which I think is actually more interesting and has some chance of being true. Okay, so as we already just commented, providing a context is a form of currying. That's not an analogy, that's strictly true. So currying is where you have a function with multiple arguments, let's say 2, and you fix one of the inputs and thereby get a function of one variable. So that process is called currying in the programming language literature, or it's also a phenomena in just Cartesian closed categories. Right? Okay, so you can see that this function on the left here has produced a new function by providing some input. So providing a context is a form of currying, which produces a new model, the one on the left-hand side in the previous line. And we can ask if this model is a transformer. Now this is a more general question. Of course, if question 1 were true, the answer would be yes to question 2. Question 2 says, does there exist W prime such that when you curry, you get another function of the same class? Okay, so if question 1, positive answer would imply a positive answer to question 2, but question 2 is much more general. I hope that's clear. And if that is true, how does W prime relate to W? And let me just sketch why question 2, if there's a positive answer, why that's quite profound. So what it means is that when you're feeding large amounts of text that is made up of subdistributions to something like a transformer, I'll say more about this in a moment, but I don't want to outline the high-level idea. Each subdistribution will correspond to perhaps a W prime, right? And training the model on that subdistribution will be doing something like training or exploring the posterior for that subdistribution in a different part of parameter space to the model itself, right? The overall weights of the original model, like the transformer, the W. W prime is something that is determined by the data, right? Maybe there's more than one example here, but W prime is a function of the context. So this is the basis for perhaps a picture of, and maybe I'll put this on the next board. It's a bit speculative, but okay, so here's a speculative picture, which you might call transformer as UTM. Not quite universal, but okay, so here's the idea. So think of the original weights, so the full transformer, as the UTM. And from the point of view of singular learning theory, so this corresponds to some very complicated singularity. So here's the mother singularity W. But what actually happens when you make a prediction well, there's some text, and then along comes something like this. And if question 2 is correct, then once you've seen this, you're actually no longer really at W anymore. Effectively, what you've done is move to another part of the parameter space and you're generating predictions from, it's the same parameter space, right? You're generating predictions from a model that behaves as though it has weights W prime. Now, if you see that context every time you see the next example Y, then you could imagine that gradient descent, if that's the way you want to think about it, or the Bayesian posterior, near that W prime, the effective Bayesian posterior for predictions of that subdistribution that's conditioned by this sequence of x's, the effective Bayesian posterior, or the effective behavior of gradient descent, is actually characterized by this subproblem and by this singularity. So it suggests a picture perhaps in which parameter space is just dotted all over with these W primes, and the mother singularity W is just kind of redirecting queries to these child singularities that live all over the place. Okay, so that's the kind of picture that, I have no idea if that's true, right? But that's a speculation which maybe gives you some idea of why it's so important to understand what in-context learning is about. Okay, so as I said, I don't think question 1 is very plausible. Maybe I'll just briefly say something about the papers which inspired this seminar. The references are in the Discord, and I'll circulate some notes for this later. I won't read them out. So they make claims that in some, like under all sorts of approximations that a single step of gradient descent looks like what you get by prepending this context. So they would say the answer to question 1 is yes. I just don't find this plausible. I mean, the math is correct, but under many, many assumptions. And I'm not sure I really buy the experiments, although maybe they're interesting. Here's an example that just maybe gets you to understand why you should be skeptical of question 1. Okay, so certainly it's false if the y's and the x's come from very different distributions, right? And it's just hard to understand. I don't see a way of getting from the approximations they're making to a more general argument. So, okay, maybe I shouldn't say I think it's false, but I'm not convinced by the evidence put forward so far. We can talk about it later, but I don't really want to dwell too much on those papers. I want to give you some idea of evidence for question 2. Okay. So, what does it look like to do multi-headed attention when you have a context? So what we're going to do is just repeat the diagram from earlier, but add in more nodes.
Sorry, Dan.
Yeah.
Can I ask a question just to check if I understand question 2?
Sure.
My question is, so the formulation of question 2 as written on the board would seems to be like trivially yes, because, well, if the original transformer can learn a language model and we are drawing y from a more restricted set, then clearly there exists a w prime that learns that. So I'm guessing this is more than existence. Like this sounds to me just like this is universal approximation.
Yeah, that's a good point.
Kind of thing.
Yeah, the way I wrote it down, I mean, I'm mixing up the role of the algorithm with the function. So what I mean more like is that are the algorithms similar in the sense that the way they compute on the representations involved similar, not just the input-output behavior. That's right. So you could make some argument based on approximation that there exists some w prime such that the overall functions are similar. Perhaps, right, because w prime is only some subset of the weights. So what I'm saying is that you only get to change the attention weights, first of all, and you could ask for, at each stage of the computation, perhaps, the entities are close to the corresponding entities, rather than just the final predictions are close. Does that make sense?
So, effectively restricted changes from w to w prime. Like w prime is not just a function of a context, it's a function of a context and w as well.
Oh yeah, I guess that's
not quite w, but
it depends on
then,
w.
like
That's
there's right. Okay.
Yeah. Any other questions?
Is that similar to requiring w prime to be close to w, so that it's some kind of local step, even if it's not a gradient step?
Yeah, it might be. I'm not sure I want to even commit to that. So this is a bit of a silly example, but so the idea of the treacherous turn is that when you see this prefix, TW prime is suddenly very different to TW, right? So you could imagine contexts. I mean, in the case where they're drawn from the same distribution, maybe you'd expect W prime to be close to W, and then the direction that relates them, then it's more like you map contexts to directions, right? And maybe that's then, you could imagine that in this picture, perhaps there are many nearby singularities, and you kind of are you're kind of selecting which one to move to with some small update. So yeah, I don't know the answer to that.
Why does in deployment as a prompt necessarily move you to a very different place in parameter
Yeah,
space?
sorry. Wait space, yeah. Yeah, it's a bit of an inside joke. So in AI safety, there's the idea that a system might somehow learn to detect that it's in training and be very friendly in training, and then as soon as it gets out of its box, start misbehaving. So the idea would be that if it sees in deployment, then it suddenly starts behaving very differently.
Right, thanks.
Okay, maybe I'm going to skip the picture.
One last question.
Yeah.
So there are like, thinking about the domain of language, there are many examples where, like a bit like the one you just explained, where if you see a particular token, that's going to kind of radically change how you respond to future tokens. I wonder if there are like similar examples where a particular token that you're going to make a gradient update on is going to radically change how you respond to future tokens.
Yeah, this is where I think...
It seems like...
Sorry, go.
Yeah, I was just going to say, it seems like, for example, because, gradient steps are local, I have this feeling that it couldn't be... There could be some things that you could do with an in-context step that you can't necessarily do with a gradient step.
Yeah, I think absolutely. So I think probably in-context learning is strictly more general than local learning. It may be that any local gradient step can be sort of mapped back into some appropriate context. I don't know, but it does seem like a more general operation. The case in which it's... So we've just discussed kind of two different kinds of contexts, right? One is, like my somewhat tongue-in-cheek example, or something else that says, now prepare to answer a calculus question, and prior to that you were discussing philosophy. Some sequences of tokens like that almost certainly are not local steps, right? So they don't seem very local. They change the behavior in some significant way. So maybe those are like these steps that I've drawn on the right-hand side. But you could then imagine that if you see, okay, now we're talking about calculus, and I give you calculus problem 1, calculus problem 2, well, maybe those are actually kind of local steps that are more like gradient steps. So maybe some kinds of contexts do provide local steps, and that, to be fair, is what those papers are talking about. So they set up a particular kind of they assume the softmax is linear. They set up a particular kind of loss function. They're assuming a linear model. They set up a particular kind of data set, and they show that these two things mathematically are similar. So there's some evidence, and also experimentally, that for particular kinds of contexts, there is something similar between in-context learning and actual gradient steps. But I think the more general concept is probably more interesting.
Here's another example that I think is a little bit easier to think about. If you assume that the language model is kind of like good at following instructions, if you give it the token repeat after me, then it turns into the identity function.
Mm-hmm. Yeah.
Which is very different from a language model.
Yeah. Okay, so here's my entities. They get embedded, and then after that there's attention. and I want to distinguish between, so this here is the context, right? And this is my new question. Okay, and then I have attention. So information is propagated from left entities towards every entity to the right and itself in multiple rounds. Now, the arrows that are of concern to us right now are the arrows that go from these kinds of entities over here. Right? So from this left-hand group into the right-hand group. If those weights were all 0, then you would just have the context computing on itself and your question computing on itself, and that would just be TW, right, with no context. So the prospect of in-context learning is to do with this overlap, these purple lines. Okay, so what I'm going to do now is write down the equations, and we'll do some playing around with them and see if we can think about these purple lines. Okay, recall the update rule for entity EI is EI prime is EI plus the sum over J, the softmax, query for I, key for J, then the denominator Vj, where Qi is some matrix times EI, Ki is some matrix times EI, Vi is some matrix times EI. Okay, so these EIs, these are the entities, these are the primitive objects which you think of the transformer as computing on. Queries, keys, and values are extracted linearly from those things. They generate queries, keys, and values, and then we get this formula. Okay. So let's play with this a bit. So that means, let me call it delta EI, which is the change in the ith entity in a single step of attention. So let me factor out that denominator. So I'm going to split the sum. I'm going to split the sum into bits that are from, let me draw a box. So imagine this is, I'm going to call these entities frozen, for a reason I'll explain in a moment. And these are unfrozen, or just normal. And I'm imagining my entity I is in here somewhere. Right. So I'm in some layer of attention, and one of the normal entities, so the entities that are involved in actually, I mean, remember that I'm going to, at the end of this, I'm going to get an output here, and that's going to give me a distribution which I'm going to sample from to make my prediction of the next token. So fundamentally I'm operating on these yi's, and EI is one of them. Okay. Now the J's range over all entities, including both frozen and unfrozen. And the reason... Are you not seeing updates on the board? Yeah.
No, I see the big curly bracket open and then nothing.
Okay, yeah, I'll look into the logs later. Yeah, thanks.
I can't see that.
You can't see it either. All right. If you try opening the board, do you see it when you open the board?
Wait, is it because Dan went back aboard?
Oh, I see that.
Yeah,
Oh.
Dan went back to the first board of the group, and maybe. So I saw both because I was looking on the orb cam.
Oh, I was looking on the orb cam too. Sorry, that was probably me.
Do you see triangle, square, love heart?
Yep.
Okay. Good. Okay, so I'm going to split this sum into two sums. One is over j frozen, and one is over j unfrozen. Maybe just call them normal. Okay, and these are the purple lines, right? These are messages, the VJs, received from frozen entities to update an unfrozen entity. And those are the ones we want to understand, right? Because that's the difference between TW and TW with a context. I hope that's clear. So the difference between TW computing Y and TW with this context computing Y lies precisely in this attention. And it's over multiple rounds. So once it's run a few rounds, it could change all the entities in the right-hand box, the normal entities, and then maybe who knows what's going on. But if we're just going to analyze a single iteration, what's happening with the normal entities is the same as it is in TW, and the purple stuff is the stuff we have to understand. Okay, so I want to explain what I mean by frozen. So we are going to assume there's going to be a bunch of assumptions and approximations. I'm not saying this is like some cute initiation of an investigation. Right? So we're going to assume all entities in the frozen box are frozen past some layer. Okay, so maybe near the bottom of that diagram, compute, but then after some point, let's assume that the EIs, or rather EJs for j less than or equal to L plus 1 are fairly stable. They don't change much. Okay. In particular, that means the VJs, KJs for those entities don't change. Right? They're frozen. Okay, so let me say something about some special cases before we do, a special case before we do a more interesting kind of calculation. If you haven't thought much about attention, maybe it's worth knowing that in sufficiently high dimensions, you randomly sample two vectors and they will be orthogonal with probability 1. Right? If there are many directions in your space, most vectors are orthogonal to each other. So you should think of the queries and keys as being in such a sufficiently high dimensional space. So unless there's some particular reason for a query vector and a key vector to line up, this dot product will be 0. Right? That's the kind of generic case. Something has to be arranged, and imagine the weights are initialized randomly, so that when the transformer is initialized, all these things are orthogonal to one another. It actually has to tune things to get them to point in the same direction. Okay, so if qi.kj is approximately 0, it can be large and negative, right? You can tune entities to ignore actively other entities. That does happen in practice. But this is the generic case. So if qi.kj were approximately 0 for frozen j, and my I is fixed, this is one of the normal entities. So if this is approximately 0 for frozen j, then, and you assume that if there's some attention of normal entities of I attending to some normal entity, sorry about the cow, it's dinner time. Well, then those first sum ends will just drop out. So you'll get approximately the sum over u not frozen. So it'll just look like the attention as though the context isn't there. Okay, which makes sense. So this is i.e. just what TW would do. So this is the case where the context is irrelevant. The entities that are in the context, just the transformer has learned that there's no particular relation between them and the entities in the question, in which case you just get TW back. Okay, so I guess in that case the answer to question 2 is yes. TW is TW prime. Okay. So here's a more interesting situation. Okay, main case for us. Still a very special case. Suppose that for each frozen entity J, remember these are frozen, they're not changing from layer to layer. Let me call it T. There is an unfrozen index AT Okay, so we're talking about a single layer of attention, right? So EI is being updated in some layer. Suppose in that layer, so in each layer there's different attention weights. Suppose in that layer the value vector for the entity EI, for the how should I say this? So here's the frozen entities. Here's T, so these are frozen. All the entities are going to attempt to pass information to EI, right? So we're all trying to pass information to this guy. That's what the update is about. Now I'm supposing that for each frozen entity, so it's got some value vector VT. I'm supposing that in this particular update, there's some entity over here, J, whose value vector is close to that one. Right, so that's J is AT. I'll say, I sort of have some idea how you might weaken this hypothesis, but we're going to stick with that for the moment. Is it clear what I'm assuming? I'm not convincing you it's reasonable, but is the assumption clear? Okay. Then we can write the update by grouping the things with similar value vectors. Right, so just take the formula on the left-hand board and merge the sum over frozen J's, or frozen T's now, into the other sum. So now it's a sum over J normal, the original coefficient, plus a bunch of new stuff. This is all the T frozen who want to be friends with J. So AT is J. Okay, and that's all times Vj. Close bracket. I hope that's multiplied at the end there. All right. So now we've got a sum of exponentials, and it's a standard trick to do at this point. So the log sum exponential is by definition what it says. So take a sequence of n real numbers and take the logarithm of the sum of their exponentials. This is commonly used in machine learning as an approximation, a smooth approximation of the max function. The error term is of the order of log n, so well, it is log n. So if the values of xi are large relative to n, or rather log n, this approximation is pretty good. Okay, let me call that x star. Okay, so let's write, I just want to take that term in the brackets and rewrite it as a single exponential, right? And the point is just that it looks like the largest one, I guess is the point. So if I let z be the log sum exponential of all those exponents, well, if there is a clear winner, then that will be approximately the clear winner. So that's my second hypothesis, that in any given update, maybe that's one of the unfrozen entities, right? Has the largest dot product and it's separated from the others. Or maybe it's a frozen entity. So in the case where there's a clear winner, the gradient update looks like this. And in the case, well, you can do much better than this. This is not entirely unrelated to some of the things that Ben was talking about in his seminar talks on renormalizing Ising models, right? But okay, for the moment, this very rough calculation gives you that the gradient update looks like a sum over the non-frozen entities. So if we reduce this update from a tension that included information from both frozen and unfrozen to an update only referring to non-frozen or normal entities, but with some modified weights. So this is a tension. Over the normal entities. But with modified key weights. WK. Right, because KJ has changed to KJ star. Now, if you actually did this calculation properly, you would sum over all the value vectors for the normal j's. You would take contributions to each one you would cluster the frozen entity value vectors by those that are closest to VJ, and then you would incorporate, rather than just taking the max like I've done here, you can do this in a more sophisticated way. Probably, I haven't done it, but you see the idea, right? So by reducing this sum to a sum over normal entities, we've effectively replaced the key weights, the original key weights, by some modified key weights, and we've got so call it WK prime, and with W prime We didn't change the query weights, we didn't change the value weights, although those would also change under the prescription I was just outlining. Okay, at least in this particular step, we had that TW prime of y was similar to TW of x, xl plus 1 y. I hope that partly answers your question, Edmund. So in this case, what I'm saying is the attention works similarly, not just that the final outputs are similar. Okay. Yeah, any questions? I'll say a little bit more, but that's the kind of technical part finished, I think. So as I said, this is not meant to convince you that question 2 is true. What I want to say is this is very important. Maybe some of you should think about it and take it quite seriously, because the reasons I suggested on the slide with transformer as UTM. When we're talking about large models like transformers that contain multitudes, and these multitudes being the W primes, right? These kind of subroutines that are there to process various different tasks, we may have to change the way we think about the statistical learning theory of these systems to account for we're probably learning many things, right? It's like there are effectively many submodels that are being learned in different parts of parameter space with different RLCTs, etc., etc. So this kind of coordination of multiple singularities by a central routing singularity, if that's what's going on, this probably calls for a rather different approach to understanding the learning theory. So, yeah, I think it's this is meant to be a invitation to walk in this direction. This is by no means convincing as it stands. Okay, if there are no questions, then let me think about what I'm going to say next. Yeah, so what Ben and I were preparing was we actually spent some time thinking about actually computing the gradient update. So if you back propagate an error, like I was showing on the first board, through the transformer to a particular weight, then you can compute what that is and try and compare it to what you get from the change from in-context learning. But I feel like that's kind of more into the details in this line of investigation. Maybe makes sense for a future seminar. So maybe I'll stop there and open the floor for discussion. Maybe let's go back to this interesting slide. Yeah, so I thought about this for the first time today, but it could be quite interesting to think through what it means to effectively learn submodels using a central model like this. Like what is how do these Bayesian posteriors fit together? I think there was a question.
I have a question. Yeah. Is the transformer, do you think, the simplest model where it's appropriate to try and study this? Because let me propose something. I was just thinking about what we said at the start about currying and LCM sequence models and stuff, but actually I think you can kind of think of any multi-input model as you can think about currying it. So I wonder if you could also think about it in terms of routing submodels and stuff. So for example, let's just say you have two inputs and you're learning a linear function, then the first input sort of takes you to a particular slice of that function, which is going to be another linear model, and thus determines like which subregion you're in and how you respond to the second input. So yeah, that's an example. I wonder what you think of it. I wonder if you think it kind of is complex enough to capture the essence of this, or if you think there would be anything simpler than a transformer that would do it.
I see no reason why there wouldn't be. Yeah, it would be difficult. I mean, okay, if we just take one one attention layer on its own without all the other stuff, that's a relatively simple model. So maybe that's maybe you can do simpler than that. But it's possible even just a single attention layer. So that's just some linear, just some matrix multiplications and a softmax. Maybe that's enough. I don't know. I mean, the model you're proposing is simpler still. Yeah, I mean, I think it's a good idea to look for the simplest example for sure.
Would such a simpler model still need to, it still needs to demonstrate in-context learning empirically somehow?
Yeah.
To be real.
I guess maybe that would be nice. I suppose the way theory often works is that you find the toy model that maybe doesn't even have the particular behavior, but like you can see a theoretical signature of something that might be relevant. So it certainly wouldn't be satisfactory to stop there, but maybe as a place to get started. It seems unlikely very simple models are going to show some interesting form of in-context learning. I don't. Well, I'm not sure. I'm not aware of a literature that sort of suggests that this is a very common property.
Yeah, I guess my proposal would be try and, in the simple model where you can keep track of the number of sort of moving parts just all on a page, try and like draw that speculative diagram to clarify the concepts and make sure you're not like making some kind of type error or
Yep.
you know, like at least to me that would be helpful. Like what, for example, does this singularity routing look like when I'm actually talking about a model with a handful of dimensions, and I can kind of visualize it rather than just sketching some abstract projection of like a high dimensional space. Yeah, that's the proposal.
Yep.
And then you know what you're looking for when you go up to the practical scale models.
Yeah, I guess you could even just take a one-layer 10H network, but with some kind of repetition of weights, right? I mean, the point here is that the model can handle arbitrarily long input because there's the way that the weights are used is not dependent on the index of the entity, right? The weights.
Yeah, that's important. Yeah, like my example of just a two-dimensional thing. When you give one input, you're left with a one-dimensional thing. So that seems like a problem.
Yeah, I think that's a good idea. Maybe we should cook up some very simple thing.
Super simple. What about like maybe like a recurrent neural network that you are allowed to do for like 2 recurrences or something?
Yeah, that's independent of the index, but in a different way. So I don't know that the iteration. I mean, of course, the distinction between an RNN and a transformer is somehow that the transformer is wide rather than deep in that way. So I think that's yeah. I'm not sure it would be simpler. I mean, it seems to me just a one-layer attention model. I mean, a single attention model would be simpler than having an RNN do it.
Yeah, you're probably right. I have another question, but I'll let anyone else jump in.
I was going to ask about the singularity explanation you gave on the right-hand side of the board. Why is it that you think these other singularities in blue are simpler? Is it because that Is it to do with the paper showing in-context learning outperforming
Oh,
fine-tuning?
yeah.
Or was it another reason?
This is just completely made up. So this is my intuition that I'm sharing. But the intuition is that effectively what W does is it maps contexts to, or you might say sub-distributions. So you have all the data that the model sees, and then within that data are various sub-distributions, like English versus Chinese text, for example. Some amount of samples are sufficient to figure out which sub-distribution you're in. And arguably, according to this intuition, I don't know if this is true, but you could argue that what a transformer is learning to do past some point in training is not actually answer the question, but learn how to map contexts to submodels. Submodel's a bad word for it because it's in the same parameter space, but I mean map contexts to singularities or like some region of parameter space, right? So the transformers, like the purpose of W, this original routing singularity, the UTM in this analogy, is to see X and produce W prime. And W prime is the model what determines TW prime, which is good at answering questions about X. Something like that. Yeah, you know.
Okay, thank you.
Caveat emptor, as they say.
Does anyone else think of the original, the transformer TW, given a point in a vast weight space W, as, I mean, as a gigantically complex joint distribution of all possible sequences of tokens, and therefore given a prompt, you're conditioning. There's a conditional distribution,
That's right,
which
yeah.
is kind of smaller than the full joint, which is what came to mind when I saw the simpler or smaller singularities in your
Yeah,
speculative
that's
diagram.
exactly what I'm thinking. Yeah. The interesting thing is that the weights are all the same weight space, right? Which is the sort of interesting novelty here.
Yeah. And I confess that I kind of struggle with the word learning in context learning. Well, in fact, that's what this whole seminar is about, right? It's all we're really doing is conditioning, evaluating a conditional distribution.
Well, but you're learning to
but it
map
works.
contexts to, I mean, okay, you could say it's a conditional distribution, but you don't actually know what to condition on, right? You're not actually conditioning. So the task being performed here is arguably to map a context, which is a very, I mean, I don't know, it's much less than you'd need to condition the distribution. And you don't know the distribution, right? So maybe that's the point. So if you knew the true distribution, you could condition on it or on some, but I don't think it's...
But it does live in the I mean, it's fully determined by W, isn't it?
Yeah. But it's... Okay, so the space X on which the distribution is living is... Okay, so that's sequences of some length, right? That's the distribution. So we're mapping a parameter to... I mean, it's like the distribution that's given by Tn, right? It's for some fixed n. And then you're saying if you fix some of those values, then that's conditioning the distribution. That's true.
I have an interpretation, which is like, which is that if we think of learning as just some algorithm that takes in data or train examples to another algorithm that produce prediction given further data, then I'm guessing the TW, the transformer itself, is the learning algorithm. It takes in training data, context, and then produce another algorithm that can take Y and produce next token. So like the transformer is the learning machine. It's no longer being learned.
It's wrong for me to. It's a distribution generator, not a distribution implicit in the W, I guess.
Yeah, that's right.
Sorry, I didn't mean to. Oh, that was too loud and it echoed. I just spent a moment on the psychiatrist's couch with the word learning.
No, I think it's right. I mean, that's well, I guess learning doesn't necessarily have to mean gradient descent, but you're not saying that either, right? You're just saying that
it means moving to a different point in W, at least in a priori to me, or in the grey book, for example.
I agree, but then if question 2 is true, then that is exactly what providing a context does.
Yeah, I completely agree.
Yeah.
I think Matt had another question.
I wanted to say I just continuing on the on what Russell I think mentioned just now, which is like even in the grey book, learning is not moving to. It's kind of critically not moving to a different W, because it's Bayesian. The learning process in W is producing. So take example, produce posterior. I'm echoing. Take example, produce posterior, and then average over posterior whenever you get a new input. That's the learning process.
Yeah, one thing I'd like to think through is what this picture means for the posterior. So maybe to take a simple example, maybe we get nowhere with this, but it might be interesting. Suppose that the context switches you, it's just a hierarchical distribution. So you flip a coin, and if it's heads, then you roll a 6-sided dice that's normal, and if it's tails, then you roll some biased dice. Okay. So if you have a hierarchical distribution like that, and you see some information that tells you which distribution it's from, maybe I don't know what that means for the relation between the kind of overall prior posterior concentrated around this W, sort of the overall model, versus you could imagine having submodels that are learning the parameters appropriate for each of those two components of the hierarchical distribution. You know what I mean? So, under this picture, the speculative picture on the right-hand side, the learning at some point, once the transformer has acquired this configuration, the learning that's happening near W, if you like, is more about routing than it is about actually solving any one of these given problems, right? So W prime becomes very good at predicting the next English word, and W prime becomes very good at predicting the next French word. And then the original, what W, it's not so clear that it's actually solving any of those problems individually. I don't know. Matt, you had a question.
I'm not sure anymore. I too am sort of struggling with the thinking of this as learning versus just conditioning, but I think that's I think it's both. I don't know if this is helpful to anyone else, but I think it's like a perspective that you can take on what's going on. Like a currying thing, where you can view a function of two arguments as taking them sort of both at once, or you can view it as a function that takes an argument and returns a function that takes an argument that returns another output. So yeah, I just think like if you accept this is a perspective, and then the question isn't like which side is right, which way to view it is right. It's more like which way to view it is useful for a particular thing that you want to get out of the model. If we want to start prompting these models as a way of tuning them, then and we want to have like a theory about that process, then probably we should try and view it as learning and see how it relates to our existing knowledge of statistical models. Like, what kind of statistical model is this? What is the parameters? And the question that Dan is asking is something like, it is the same model. Like, it's just the transformer model, as if we were training it, as if we were fine-tuning it, and tuning the weights. Yeah, maybe that's true, or maybe it's not. Either way, it's like something. There is some kind of implicit model there, and it would be useful to try and understand it, perhaps, from that perspective.
Isn't fine-tuning... Oh, sorry, you go.
No, go on then.
I'm just wondering, because at least my understanding of this is that in context learning is kind of fine-tuning the entities as opposed to the W parameters, which are getting multiplied together. So it's still like, I guess, indirectly updating the W parameters by the entities. And so I guess I still think of it as learning.
Yeah,
it's still kind of changing. W.
Yeah, I think that's right. I mean, that's when you look at how the transformer processes its input, layer by layer, I think by any reasonable definition, it's learning, because at the beginning it just knows each token, its universal embedding for that token, right? It doesn't, in the sentence, know that there's any particular relation between he and Matt. But over the course of processing the tokens and its experience in predicting the next token in English language, it comes to acquire the information that he refers to Matt, and that's represented explicitly in the entities themselves and the directions of these query and key vectors. That information transfer is learning. It's not learning that sticks around for the next example, but I don't know, it's information acquisition maybe. Whether you want to call that learning or not, I'm not sure. So the statement here is that form of information acquisition may in some case look like the form of transfer of information that you get by gradient descent, which is also accumulating information from the data into the weights, just in a different way.
So suppose an angel comes down and hands you this function W prime of context. What now?
What now? Well, I'm not sure what you're asking.
What would you do with it? Like,
well, apart from what the transformer itself does with it, which is predict the next token, you're asking like what would a better understanding of this mapping, what implications would that have for analysis of transformers, for example, or understanding the algorithms that they're executing? Is that the direction your question is going?
Yeah, exactly.
Yeah. Well, so you could then look at W prime and try and understand. I mean, it's just to some point in parameter space, right? But if you were to formulate the subdistribution, so the particular y's and the map to the next token as its own learning problem, right? So within the original training distribution for the transformer, take these subdistributions you can formulate them as independent learning problems with the same parameter space and take their KL divergence, and W prime would be a singularity of that KL divergence. And you could then understand its properties, and that would be kind of like a way of decomposing, arguably in this storyline, these W primes are all like subroutines, which are combined in some way to be executed. And if you could analyze them independently, it would be like a divide and conquer strategy for understanding what the overall transformer is doing. So maybe we have more chance of understanding what these components are doing and their theoretical properties if we can. Maybe they're not 100 billion dimensional, right? Maybe there's a much lower dimensional subspace in which these things have their meaningful degrees of freedom or something. I don't know. I think what your question just reminded me of is it's quite important to note that if question 2 is true, that means that, keep in mind that if you allow the transformer to read the tokens that it predicts, right? So you predict the next token and then you process the sentence with that token in it, which is the usual way you interact with GPT-3, for example. By predicting tokens, it can condition its own model, right? So under this scenario, if you're feeding many tokens into GPT-3, it can actually move itself effectively to different parts of the parameter space. So it's quite important then to understand where those places are that it can go, right, if you want to understand what it's doing or what it's capable of. I think that the possibility of internalizing the learning process in this way seems quite significant for understanding what's going on inside the model. And from a theoretical point of view, it might be kind of futile to study W itself, right? I mean, we train the model, it's some very complicated singularity. We probably have very little chance of saying anything directly about that, but maybe there's some chance of saying something about the W primes. I don't know. Okay, we'll have to wrap up in a few minutes for the next seminar, but we can take one more question or comment.
I just wanted to remark on what you said just now. Also, I think this in-context learning thing seems like an important thing to understand. Did someone say before that they showed in-context learning outperforming fine-tuning in some setting?
I think it's not by much, but a little bit.
Okay. Yeah. Well, I mean, it's okay. So, I mean, I won't take that as like super irrefutable evidence that it's always better. But okay, let's say we want to use these models more. Prompting them is a very natural way to interact with them and kind of tune them to do what you want. So this might become either alongside or even potentially in replace of a way to train and improve models than through gradient descent. If you could, I mean, there's only so much prompting you can do because they have like a finite sort of architecture size. But if you could find some way to store the prompts changes on the model in the weights, then that removes this limitation. So if we had access to that function, you could then kind of use it in order to make this prompting method of training the model or changing the model, could make that a kind of predominant way in which the model is actually improved. Like I said, either alongside or in opposition to using gradient descent. And so then understanding it is like just as important as understanding how gradient descent changes the model.
Yeah, I think that's true. Just a small practical note. I mean, there's two ways of making use of GPT-3 through the API that OpenAI has provided. You fine-tune it, or you just provide it with context. And the latter is what people do. I think very few people actually cost more money. It's more of a hassle to fine-tune. The whole field has kind of moved away from fine-tuning towards prompting. So this is like in practice the way people interact with these systems. I think That's my understanding.